Okay, so we're going to have a look at ionization energy. So we sort of finished last session with ionization energy, and we're going to look at it a bit more. So ionization energy and ionization itself is the we're looking at, well, ionization is obviously just the energy that we need to remove ionization energy, sorry, it's the energy that we need to remove one electron from an atom. So ionization is just basically the removal of an electron. So we talked about those ionization equations last session, and about ionization is the removal of one electron from an atom. And then we will end up with, our product would be an ion and a free electron. And so we can talk about ionization energies in terms of first, second, third, fourth, fifth ionization energies. So first ionization energy, we're removing one electron. Second ionization energy, we're removing second, and so on. So ionization energy officially is has an official sort of what's the word I'm looking for? Official definition. That is it's the energy required to remove one electron from each atom in 1 mole of gaseous atoms. So we spoke about this last time, that whenever we're dealing with ionization, the atoms are in a gaseous state. So it's the energy required to remove one electron from each atom in 1 mole of gaseous atoms to form 1 mole of gaseous 1+ ions. So it's basically the energy to remove an electron from an atom to form 1 mole of ions. You'll have done a little bit about moles at GCSE, and obviously we know mole is a unit of measurement. It's officially the amount of things there. So we could actually have moles for the moles of shoes, or the moles of, you could say I have a mole of fence panels. It's a set number, which obviously is the Avogadro's constant of 6.023 times 10 to the power of 23. So we can officially have an exponential amount of moles in anything. But we use moles for atoms, and we'll do moles a bit more in detail next week, and do some mole calculations. So lots of that's revision from moles at GCSE. But yeah, at this moment, we're just talking about 1 mole being 1 unit of atoms. So ionization energy, it's basically just the energy that we need to get rid of some electrons from an atom. We measure it in kilojoules per mole, and we give it the abbreviation IE. So if at any point I start writing IE, rather than ionization energy, that's just the shorthand for it. Ionization energy is really interesting because actually what it does is it tells us a lot about that electronic configuration of our elements. So actually it tells us a lot, and it proves and gives us evidence for shells and subshells and orbitals and the pairing of electrons. So actually all that electron configuration we did the other day, it will actually fit in really, really nicely with ionization energy and how they work together. So why are we not moving forward? That was not helpful. Right, here we go. So successive ionization energies, we're going to have a little look at first. So what we mean by that is we can measure the energies required to remove each electron in turn. So for example, if we had magnesium, the first ionization energy would be the energy required to remove 1 electron. Second ionization energy is the energy required to remove the second electron, and so on and so forth. So we can measure the energies required to remove each electron in turn. So hence they're successive, because we measure one, then we measure the next and the next and the next. And obviously we go from outer electrons to inner electrons. So we're not losing any of those rules about how we lose our electrons. But when we are removing electrons from an atom, we obviously work from our outer electrons to our inner electrons. So what we end up seeing is a pattern like this. So we have our first ionization energy down here, and it's in the third shell. So we've got 1 atom in the third, 1 electron in the third shell, and that has the lowest. You will always find your first ionization energy has the lowest, first ionization number, sorry, has the lowest ionization energy. So your first ionization has the lowest energy. And it builds up as we go. And the reason that we're doing that is we're going to look into that now, is things about basically, if we're starting from the outer electrons and working our way in, it's all about the electromagneticity of atoms, and actually those interactions that the electrons and protons are having in that positive and negative charge. Again, it's all around this positive negative charge and how easily we can lose them. But basically what ends up happening is we lose, for example here, 1 electron from the third shell. Once we've lost that electron from the third shell, we have a big jump in ionization energy. It takes a lot more energy to get rid of the next 8 electrons, and they're all a little bit harder than the last one to get rid of. Then we have another big jump again to the next shell. So again, these, first of all, the first thing we can start to say is these big jumps between the third shell, second shell, and the first shell are showing actually that there are evidence that these shells do exist. We're talking about shells. We say, oh yes, we have these energy levels, these energy shells. The electrons are in around our nucleus, but these are actually proof. These start to prove that. So to form a positive ion, we need energy to overcome the attraction from the nucleus. So the nucleus, as we've talked about quantum theory last time, the nucleus is a ball of positive energy, and we obviously have electrons are negatively charged. So to form a positive ion, we need energy to overcome that attraction from the nucleus. So each electron, as it's removed from an atom, the remaining ion becomes more positively charged. So we've lost a negative charge, so the atom overall becomes more positively charged because we have that unequal balance. We've lost an electron, and not usually our electron and proton number would be exactly the same in an atom. So we've lost an electron, so then we have a more positively charged atom, hence it becomes a positive ion, and so a cation. So removing the next electron away from the increasing positive charge becomes more difficult. And it becomes more difficult because actually the center of this, the nucleus of the atom is now so let me word this actually. The atom itself, the overall atom, the ion itself, is now more positively charged than it was before because it's lost a negative charge. So that positive charge is going to be increasing. So whilst it doesn't change as such as we're getting more protons, the proton number stays the same, but as we're losing a negative charge, it means that this positive charge becomes stronger. And so what happens is, as we lose electrons, this positive charge becomes bigger and bigger and bigger, and that has more of a pull on these electrons, and it doesn't want to lose them more, so it has more of an effect there. So our ionization energy gets larger each time because we need more energy to remove these electrons, because it's harder to remove them because the nucleus is becoming more positive. So this is how we would write successive ionization energies. This is very similar basically to what I was showing you the other day on how to write ionization energies. We obviously have sodium into Na plus and an electron. Then if it's the second, so that would be our first ionization energy. Our second ionization energy, we have Na plus into Na2 plus an electron. And then third ionization energy, Na2 plus Na3 to Na3 plus an electron. So over here, these are showing us our values, the actual energy that is required to remove that electron. So the first ionization energy is 496 kilojoules per mole. And then we have this huge jump that's basically 4,000 kilojoules more. And we go from just needed 496 kilojoules per mole to remove an electron to, for the second ionization energy, it being 4,563. Then we have another jump to 6,913. Still quite a large jump, but nowhere near as much as the first time. So we always start with the end product of a previous ionization energy when we are writing successive ionization energies. And this is possibly the most important thing. We talked about it the other day, but we must include the gaseous state when writing ionization energies, because ions only form when in the gaseous state. So marks will be lost, or you just don't even get a mark if you're asked to write. For example, write the first ionisation energy for sodium. You write it, but do not include the state symbols and the correct state symbols, so the gaseous state. You can just end up basically getting no marks, because this is really important. It's one of them parts that GCSE you'd probably got 2 marks. Here now at A level we're saying no, it's 1 mark, because you need to know that it has to be in a gaseous state. So that graph that we're looking at, we can see evidence for electron shells. So this is a graph for sodium. So we've been talking about sodium going up, losing its electrons. So sodium looks to have 1 electron that's easy to remove. So this one was our first ionisation energy, and that was 496 kilojoules per mole, this one, okay? So that is showing us that there is, or would imply that there is 1 electron in this 3rd outer shell. So the further away you are to the nucleus, the easier it is to lose the electron. So 8 nearer to the nucleus, they're a bit harder to remove. So this would give us evidence for our 2nd shell. They're harder to remove than the first one. And we have this about 4,000 kilojoule per mole jump up to the 2nd ionisation energy. And then we have this final jump. So the 2 very close to the nucleus, so they are the nearest electrons to the positive charge, and so they are the hardest to remove, so they have the highest ionisation energy. Now, whilst this is saying it's the 3rd outer shell, we have to remember that it's still our 1st ionisation energy, because that's the 1st electron removing. 1st electron furthest away from the nucleus, and it sort of works that way. And that's just one thing to sort of remember. So N3 means 3rd shell. So the 3rd shell is always has the lowest ionisation energy, if we're talking about only 3 shells. N2, our 2nd shell, middle ionisation energy, and then N1 always has the highest ionisation energy. So we have lots of things that affect ionisation energy. We've sort of slightly mentioned them, but not in lots of detail on this. What we're going to look at now in particular. So because our electrons are negatively charged and our protons are positively charged, we have this attraction between them. We have this attraction of the 2 opposite charges wanting to be together, wanting to pull together. So the greater the pull of the nucleus, the harder it is to pull an electron away from an atom. This is why, as we go through the successive ionisation energies, it becomes harder to remove an electron each time, because the positive charge is becoming larger, it's becoming stronger. So nuclear attraction, so this is what we're talking about here. When we say nuclear attraction is the attraction between the protons and the electrons in a atom. So nuclear attraction of an electron depends on the atomic radius, nuclear charge, and electron shielding or screening. It means the same thing. It just depends on where you're reading. Some resources, some textbooks will call it shielding, some will call it screening. Most places probably use shielding now, but you do occasionally come across some things that use the term screening, so it's worth just knowing in your mind that there's another possible word for it, but they mean the same thing. So we'll look at atomic radius first. Sometimes this is called the distance from a nucleus. Why we have to call them different things each time, I don't know. But yeah, I'm just going to pop on here. Let me annotate this a second. Atomic radius, pop it here. Oops. Atomic radius, I'm just going to write distance from the nucleus. And again, this is one of those ones that occasionally, quite regularly actually, one textbook will categorize this as just being distance from a nucleus. You'll have another textbook that calls it atomic radius, and it's all sort of the same thing. But anyway, so the greater the atomic radius, the smaller the nuclear attraction experienced by the outer electrons. It's a bit of a wordy thing, doesn't really make much sense. Basically, our electrostatic attraction, so that attraction between our electrons and our protons, this will decrease with distance. And it doesn't just decrease, it actually decreases. I'm just going to add this word on here, sharply. So when we go back, if we went back a page, which this now doesn't want to do, which is not helpful. If we go back here and we just look, these are those sharp increases. Okay, so we're going from this shell to that one. So that's our atomic radius. So we're actually talking about the distance from a nucleus. Within one shell, we're saying that the distance is the same. And we're talking about the distance from the third shell, second shell, first shell to the nucleus. So we have these sharp increases. You can see it really nice and clearly on this graph. So the further away we are, or further away an electron is from the nucleus, the less energy is required to remove that electron. So basically, the greater the distance, so if we pop this on here, so if we put greater distance, it will mean that we will have equals a lower ionization energy. That's sort of a rough idea of atomic radius. That's sort of what's happening. Nuclear charge then. Okay, so nuclear charge is that thing that I was talking about. This one really applies to successive ionization energies even more really than atomic radius. So nuclear charge is the greater the nuclear charge, so the greater the attractive force on the outer electrons. And what we mean by that is the greater number of protons, so the nuclear charge being the charge from the nucleus, so the greater the positive charge from the nucleus is, the greater the attraction of electrons to the nucleus. So we've got 3 examples here, and we've got hydrogen, helium, and lithium. So hydrogen, 1 electron, first shell, very, very close to our nucleus. But obviously we only have 1 proton, so it's only got 1 positive charge, so they're balanced with each other. So as you can see, the ionization energies here are increasing each time. Well, from hydrogen to helium, but not when we get to lithium. I'm going to explain that in a second. So hydrogen and helium, they're both on the first shell. Okay, so the atomic radius for both of these is exactly the same. So the distance from a nucleus shouldn't affect, in comparison to each other, shouldn't affect the ionization energy because they're both comparatively the same distance away from the nucleus. They are both very, very close to the nucleus. They're both going to need a lot of energy to remove them. So then we go, okay, so then why does helium have a higher ionization energy than hydrogen? Okay, well, helium has a greater nuclear charge. Helium has a 2+ charge in its nucleus, which acts on that 1 electron. So whilst it is balanced out overall, our overall atomic charge would be 0. When we're trying to remove that 1 electron, we're trying to remove 1 electron from a 3+ charge, a 2+ charge. So we have that greater attractive force on our outer electron. So this electron here is harder to remove. So our helium electron is harder to remove than our hydrogen one because of this nuclear charge. Then lithium, you might go then, okay, well, lithium, it's 3+, it's got a greater nuclear charge. Surely lithium, its first ionization energy, so that's first ionization energy must be higher than helium then. No, because we have atomic radius coming into play. So here, whilst we have this 3+, a greater nuclear charge, it is forming a greater attractive force on our outer electrons, but we have this greater distance. So we're further away from the nucleus. Therefore, the nuclear attraction is smaller on the outer electrons than on these 2 inner ones. Okay, so because we've got a greater distance, our ionization energy is lower. As you can see then probably with this, as we then go through successive ionization energies of the same atom, you can see why a nuclear charge then has a really huge effect, because actually then once we've lost, let's say for example we've got rid of this one on helium, it's going to be even harder to get rid of this second electron on helium, because we still have, we will then now have a 3+ charge on the outside, on the outside, sorry, in the nucleus, and then we would have this one electron that we still need to get rid of. So then this ionization energy then increase even higher for our second. But yeah, nuclear charge, our ionization energy is going to increase as nuclear charge increases. Then that leads us to electron shielding, or sometimes called screening. So electron shielding, this is, again, I'm using those same three examples to explain this one. So what happens is our inner shells of electrons actually repel our outer shell electrons. So this is talking about those electrostatic and electromagnetic forces again. So what's happening here is, because they all have a negative charge, we are actually getting some shielding happening. So these inner ones, so let's use lithium, for example, they're closer to the nucleus, so they are harder to lose, but actually they're getting more of that nuclear charge, they're getting more of that attraction than this electron out here, because we've already said that the further away they are, already said here that the atomic radius, the further away you are, the smaller the nuclear attraction. And actually one of them reasons is because of this screening, or shielding. So the greater number of electrons we have, and I'm going to pop this here, so our greater number of electrons between our nucleus and the outer electron, between the nucleus and outer electron, we have a lower nuclear charge. Our nuclear charge decreases. So if our nuclear charge is less, it means it is easier to get rid of it. Okay, so our positive charge is reduced by the electrons that are in between. So this basically shields, it's basically shielding this outer electron from some of this positive charge. So this one actually takes more of it, and this one takes more of it than that one. So the greater number of electrons, and it's actually the amount of electrons as well. So it's not just shells. So if we had, for example, it wouldn't be lithium, but obviously if we had some extra electrons on here, we can count these ones in there as well. But the general rule here is, for electron shielding, if we have a greater number of electrons, that means we have a lower ionization energy. So that lowers our ionization energy. So again, that explains nicely here, why our lithium has a lot higher ionization, lower ionization energy, than helium and hydrogen. So helium and hydrogen have a lot higher ionization energy because they have no electron shielding going on. Electron shielding is going on in lithium for this one, and we have atomic radius in play, distance from the nucleus. So they all affect that nuclear charge coming from the nucleus. So that's the three factors that really affect ionization energy. So let's have a little bit more look into this in a bit more detail. So we're going to look at the trends across a period now. So what happens is, this is our second and third period. So what's happening here is our ionization energy, and this is our first ionization energy. We're not bothering looking at second, third, fourth. We're just looking at first ionization energy, the energy required to remove that first electron. So as we're going across a period, so as we're going from the beginning of the second period and the beginning of the third period, what we start to see is our ionization energy. So our ionization energy increases across a period. It increases as we go across the period. So why does this happen? Well, if we think as we go across a period, our atoms are getting bigger. So what is happening there? Well, what happens here is our atomic radius is going to decrease. So our proton number is going to increase. So therefore, our electrons are going to be more attracted to the nucleus. So as they are more attracted to the nucleus, they are going to be harder to remove. So therefore, as we go further across, our electrons are getting closer to our nucleus, and so our nuclear charge increases. And I think I can show that here. Let's see what I've got. Here we go. So trends across the period again. So what we say is it has a general increase because it's not an official full increase every time. So it does drop dramatically for the start of another period. And that's because nuclear charge increases. So as you can see, we've got helium, neon, argon, krypton, xenon. So there's a general increase across the period before the value drops dramatically for the start of another period. And it drops dramatically for the start of another period because our nuclear charge is going to increase at that point. So let's have a look at hydrogen as an example. So hydrogen only has a nuclear charge of +1. But hydrogen has a relatively high first ionization energy, and that is because its electron is closest to the nucleus, so it has no nuclear shielding. It has no electron shielding, sorry. Its distance from the nucleus is really, really close. So even though it's got a lowish nuclear charge, the other two aspects of electron shielding and distance from the nucleus, atomic radius, has a massive impact. So actually hydrogen has a relatively high first ionization energy. So if we'll start here, then let's look at helium. So we're going to go across the group. So helium, we have this massive jump in ionization energy again. So what happens here is helium has a much, much higher value because of the extra proton in the nucleus. So it is harder to remove that extra electron because the extra proton is providing a stronger attraction, it's providing a stronger charge in the nucleus. So that's a stronger attraction for the electrons, making them harder to remove. The distance hasn't changed, the shielding hasn't changed, but actually our nuclear charge has changed, which means that helium is then first ionization energy is a lot higher than hydrogen was. Then we go and have a look at lithium. So we have this massive drop when we get to lithium. And so we're starting to get into the next energy shell. So whilst we have this increased nuclear charge, which will keep happening as we go along the periodic table, we have now got electron shielding coming into play. And so this electron shielding is coming into play from the 1s orbital. So because of this, the ionization energy, the energy that's required to remove that electron from the second shell, is a lot lower. The 2s electron is also further away from our nucleus, so it's held less strongly and it needs less energy for removal. So we've got shielding and we've got atomic radius in place. So even though our nuclear charge is higher, our atomic radius and our electron shielding has a bigger place. So our lithium has a lot lower first ionization energy than either of the previous two. Then we go to beryllium. Beryllium is higher than for lithium because it has an increased nuclear charge. If we've got one more electron, means we have one more proton. We don't have any extra shielding in play. So the shielding doesn't help it lower. We've got no extra shielding in play, but our nuclear charge has got slightly higher. So because the nuclear charge has got slightly higher, it's a little bit harder to remove, but our atomic radius hasn't changed, and we've got no more shielding. Then we have boron. Now, like when we were talking about electron configuration and we go, oh yeah, we fill it with the 1s orbital, then we fill the 2s orbital, then the 2p orbital, then we fill the 3s orbital, then we fill the 4p orbital, and then we fill, why did I say 4p? 4s orbital, then we fill this one, and that's the 3p orbital. We have some slightly different non-following of the patterns again. So boron is one of them. So boron does drop. This is because the extra electron has gone into one of the two p orbitals, and this is why we have proof of orbitals. So not only do we have proof of each actually energy level, each shell, each overall shell, first shell, second shell, third shell, we also now have proof of orbitals. So this outer electron on boron isn't in the 2s orbital, it's now gone into the 2p orbital. Because of this, we have an increase in shielding, which makes that electron easy to remove. So whilst it's on the same energy level, because it's not in the same orbital, because 2p orbital is separate to the 2s orbital, it's actually, that electron's actually getting shielded from the nucleus via the 1s and 2s orbitals. So we've got some actual shielding going on here. So it's evidence like this that confirmed that subshells actually existed, and if they hadn't been ace subshells, the value would be higher than that of beryllium. So boron would be probably somewhere like here, but obviously we do have subshells, and that was one of our reasonings why we could understand, actually prove that subshells exist, and it also explains why boron goes down. So here our nuclear charge has increased, our atomic radius hasn't changed, but actually our shielding has. And then we have carbon. Carbon goes up, value increases again for carbon due to increase in nuclear charge. We haven't got any additional shielding like we had for boron, because we're still in the 2p orbital. We don't have any extra distance from the nucleus, so it's just going to go up because our nuclear charge is increasing. Then we have nitrogen. It increases again because we have an increase in nuclear charge. We don't have any extra shielding, we don't have any extra distance from the nucleus. And like we said before, we're filling each 2p orbital up with one electron first before pairing them. And this also comes into play with our ionisation energies. So then after nitrogen, we have oxygen, and we have a drop in the value of ionisation energy for oxygen. This is quite interesting. So why this happens is this electron, the outer electron, this last electron, we would maybe call it, in oxygen, has paired up with one of the electrons already in one of the 2p orbitals. So obviously we filled all the 2p orbitals with one electron, obviously they can pair, it's gone up and paired. What happens here is there is a repulsive force between the two paired up electrons. Because they are both negative charges, they are both going to repel from each other. So that's really, really useful actually. And what we do is we call this whole thing electron repulsion. And so this electron repulsion, because they're paired together, they're actually able to basically repel each other more. So they're wanting to get rid of each other anyway. So actually, we've already got some repulsion force coming into play when we want to remove that electron already. So actually, it doesn't require as much energy as the last electron to remove in nitrogen, because we've got a slightly weaker charge because of this. So the repulsive force between the two paired up electrons means that less energy is required to remove one of them. Then fluorine, we're going to go up again, because actually, whilst we have some repulsion going into place, it doesn't affect it as much, because this time we've got two orbitals that are full, so that repulsion is sort of dampened down now. So the value increases again for fluorine due to the increased nuclear charge, and our 2p orbitals are almost full, so they don't have this same instability as before. Neon is going to go up. Value for increases for neon because we have this increased nuclear charge. Our 2p orbitals are now full, so the next electron will have to go into a higher energy 3s orbital. Because it's got to go into the high energy 3s orbital, we drop down again. Okay, so this is our lowest ionization energy so far, and this is because the extra electron has gone into an orbital, a different orbital, and it's not just a separate orbital, it's an orbital in the next energy level. This means we've got extra shielding because of the 1s, 2s, and 2p orbitals. And also our atomic radius has increased. So we've got atomic radius increasing, and we've got extra shielding. So actually the increase in nuclear charge is less effective here. So it's all sort of a balancing game between the three different factors that can affect ionization energy, going which one's stronger, which one's affecting it more each time. Then we have magnesium. Value for magnesium is higher than for sodium due to the increased nuclear charge. We don't have any extra shielding because we're just still filling the 3s orbital. And the trend at this point is then very similar to that at the start of the second period. So we've now go through into the next period, and it's actually the trends are going to follow very similarly. The ionization energies might be different, but they are going to follow a very similar trend. So if we have a look at this, these are our trends in period 3. So we've got sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, and argon. So our trends in period 3, very similar to when we were talking about period 2, we have this drop in ionization energy from magnesium to aluminium. So why do we have a drop between magnesium and aluminium? So we call this officially, this drop, the impact of subshell structures. So I'm just going to label this one as subshell. Oh, that's not how you spell shell. Subshell. Okay, so what happens is our outer electron in aluminium has moved into our 3p orbital. So it takes less energy to remove an electron from here than it does in 3s. Okay, we'd expect aluminium to have a higher ionization energy due to it having a greater nuclear charge, but it doesn't. So the 3p orbital is further from the nucleus. So that's the first thing. It's further from the nucleus on average than the 3s orbital. So that's quite important here. So turn my pen around. So 3p further, it's further from our nucleus than 3s on average. So because of that, we have that change in charge. So our orbital has a higher energy level and our electrons have a lower electrostatic attraction to the positive nucleus. Therefore, they are slightly, and that is the important word here, they are slightly shielded by the 3s2 electrons. So they are slightly shielded, can't remember what the other word was that we've used. I can't remember it now. Slightly shielded by the 3s2 electrons. Then if we have another look further along group period 3, we also have a drop between phosphorus and sulfur. I'm going to change my pen color actually for this, otherwise it's going to be messy. So we get a drop between phosphorus and sulfur. So what we would expect is we would expect sulfur to be higher than phosphorus because we go, well, the nuclear charge is higher. Yes, but, and there's always a but. So this is between the groups. These are between group 5 and 6. So we're swapping groups here. So what happens is there's shielding occurs in our outer electrons is identical. We shouldn't have any difference in our shielding. So if we look at the electron configuration, we have 1s2, 1s2, 2s2, 2s2, 2p6, 2p6, 3s2, 3s2, 3p3, and 3p4. So our shielding is identical for our outer electrons. Sulfur has a higher nuclear charge. So therefore we'd say, well, it has a higher nuclear charge and the shielding is the same, so it should have a higher ionization energy, but it doesn't. The reason it doesn't is because in phosphorus, our electron that we remove, we are removing it from a singularly occupied orbital, okay? So we are removing it from one that is singly occupied. So phosphorus, we're going to remove an electron from a singularly occupied orbital. And this is going back to that repulsion idea that I spoke about a second ago. So our phosphorus electron is removed from a singly occupied orbital. Our sulfur electron is removed from a doubly occupied orbital. So I'm just going to write paired here. It'll be moved from a paired orbital. So what happens here is we have sulfur with a lower ionization energy because the electron is in the same orbitals repel each other. It's the idea that they're actually repelling each other. So it's that actual extra help to get rid of it. So our electron is easier to remove from a doubly occupied orbital. So from a paired orbital, it's actually easier to remove that than when it's in an orbital by itself. So again, in phosphorus, each of our 3p orbitals has 1 electron. In sulfur, 1 must have 2. And a repulsion between these 2 paired electrons make it a lot easier to remove 1. Then we can have a look at trends going down the group. So we've talked about going across the periods, and then we can look at going down group. So this is our general trend. And again, we like to use the word general trend because it isn't always 100% the same. But here we've got the examples of group 2 elements, we've got beryllium, magnesium, cesium, and so on. So general trend is a decrease as we go down our group. This is because the outer electron is in a level that gets further from the nucleus. So we're actually in a completely different energy level, in a different shell each time. So atomic radius is increasing as we are going down our group. So our electrons are further from the nucleus, therefore there is less attraction. Our nuclear charge increases, however, it's basically cancelled out by the electron shielding from lower energy shells. So even though our nuclear charge has increased, we have so much electron shielding and we have such an increase in atomic radius that's cancelled out. So we have basically 2 things in play here. So our electrons are further from our nucleus, so there is less attraction, and we have more electrons between our outer electron and our nucleus, so we have greater shielding. And this is actually possibly one of the strongest points that provides evidence for the existence of shells more than anything else. Because as we go down the groups, we go, oh, well, the nuclear charge is increasing. Well, hang on, our ionization energy is dramatically decreasing as we're going down the groups. Now, you will see that it starts to slow down here. As we talked about last time with electron configuration, as our energy levels, as we're building our shells up from our nucleus, the gap between them gets smaller each time. So the gap between 1 and 2 is quite large, 2 and 3 is smaller, and it gets smaller each time, which then also, we should sort of have proof of why we know that distance gets smaller each time, because actually our ionization energy, the difference, our difference in ionization energy from here to here, oops, is a lot larger, a lot greater than our ionization energy difference from here to here and here to here. And that is because we have that increase in our atomic radius. We know we're going into different energy shells, but the difference in the atomic radius is actually decreasing as we're going because those shells are getting closer to each other each time, which is quite interesting, really. So you often get questions like this that appear. So we're going to just have a little quick talk through this question. So you'll often get asked things like, which has the higher value, the first ionization energy of sodium or the second ionization energy of magnesium? You can just get asked random questions like this. So the answer to that would be the second ionization energy of magnesium. So I'm going to talk through the stages of that and what we would have to do. So the first ionization energy of sodium involves this change. So what happens is our sodium is going to go to sodium plus. So we have 1s2, 2s2, 2p6, 3s1. So we are losing an electron from we've got an energy level drop. So if we look here, we're going from 3 down to 2. So if we start thinking about shielding, start thinking about atomic radius, start thinking about nuclear charge, we can start to get those ideas in our head. Magnesium, okay, it's a second ionisation energy. Normally so we know that it's going to be harder because we have difference in shielding. So first ionisation energy of sodium involves the following change. So we go from basically losing this 3s1 electron. The second ionisation energy of magnesium involves exactly the same change in electron configuration. So you might think, well, why then? Why don't they have the same ionisation energy? That is because magnesium is already an ion. So magnesium obviously starts off with 12 protons. Sodium has 11 protons. Sodium plus has 11 protons. So in the red, I'm writing the proton number. So what's happened is, whilst they have the same electron, officially the same electron being moved, they're having an electron from the 3s1 orbital being removed, the same effects of shielding and atomic radius are in play. The difference here is the nuclear charge, because magnesium has 12 protons in its nucleus, whereas sodium only has 11. So what happens here is we've got a greater nuclear charge. So because we have a greater nuclear charge in magnesium, that means that the electrons being moved are held more strongly. So more energy must be put in to remove it. Therefore, if the question was asking you the first ionisation energy of sodium to magnesium, any that sort of come next to each other where we could work it out like this, it's always going to be the second ionisation energy because it has a higher nuclear charge, because obviously our proton number is not going to change. This doesn't change when we are making ions. We don't have any change here at all. So that is the most important bit there for questions like that. And then I think another little bit of that impact of electron repulsion, just go over that again. So this is that phosphorus and sulfur idea again. So our shielding for phosphorus and sulfur is identical. We have no difference in shielding. Our atomic radius, our distance from the nucleus, whichever version you want to call that, is identical each time. But sulfur has a higher nuclear charge than we might expect it to. Sulfur has a higher nuclear charge, so we might expect it to have a higher ionisation energy, but again, that's not the instance. What happens is the electron we remove from phosphorus, again, is one of them from a singly occupied orbital. The electron removing from sulfur is from a doubly occupied orbital. It's from one of those paired orbitals. So sulfur has a lower ionisation energy because the electrons, when they're in the same orbital, they're going to repel each other. Therefore, our electrons are easier to remove from a paired orbital. That is roughly everything on ionisation energy. And so we're sort of at the end of this first, I'm just going to stop recording. So we're basically at the end